and this is going to lead us into this idea of optimization. So optimization is just finding the highest or lowest. And we've kind of done some of this already, but some questions that we are working towards being able to solve is, what shape of a can would we need to minimize your manufacturing costs? If you're going to make something, you want to minimize your costs in doing that. Or what's the maximum acceleration of a space shuttle? Or, a medical application. What is the radius of a contracted windpipe that expels air most rapidly during a cough? Or what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? So this idea of maximization and minimization is actually the reason that calculus is required by so many different majors. That's why all the business majors have to have calculus, because you have to be able to maximize your profits and minimize your costs. That's why science majors have to have calculus, because of this idea right here. We are starting out in this section, we're really just going to be looking at graphs, so we're not getting into anything too complicated yet. First, we've talked about absolute maximums and minimums before. Back in college algebra, we touched on them. I don't know if you did them in Algebra 2. I think you just did like maximum of a parabola. So, but in college algebra for sure we did it. So the absolute max or min, sometimes these are called global maxes and mins. It's just the absolute highest or lowest on your entire graph. When you are looking at these, they can be endpoints. So it is okay for those things to be endpoints. I think this is like the little box at the top of the slide, on the second slide you have. Sorry, I kind of condensed yours to fit it onto 2 sheets of paper. But the absolute could be an endpoint. When we look at it, we're looking for ordered pairs. So we will take some graphs and look at these. That's really like the first 4 questions on the homework tonight, is just looking at a graph and telling me what your absolute maxes and mins and local maxes and mins are. So we would say f of 3 equals 5. When my x is 3, this is 5. You could also just say the ordered pair 3, 5 if you prefer. You don't have to use the function notation. So that would be the absolute max. That is the single highest point this graph ever hits. Let's assume these endpoints just stop. Okay, there's not arrows there. My absolute min is right here. So if you wrote it as function, you'd say f of 6 equals 2, or if you said that's an ordered pair, 6, 2 is the absolute min. And like I said, these could be called global maxes or mins. We also refer to these as extreme values. If I ask you to find your extreme values, I'm just saying find all the maximums and minimums on your graph. So far, so good? Could a graph have multiple maximums, absolute maxes and mins? Only if it was the same. If my graph ended right here, could we still say these two are both absolute maxes? Yeah, because they hit the same y value, but that's the only way you could have more than one. What if my graph kept going down over here? What would my absolute minimum be? Yeah, so if there's not an actual number, we just say none. What if on my graph, let's say this had been an open circle. So that's the lowest point, but it's not technically on my graph because it's an open circle. So do I have an absolute minimum? No. So if it's an open circle or an arrow there, you won't have one. So you don't have to have the absolute maxes and mins. Okay, the next slide on here, it's at the top. I've got some graphs below it for you, but a local maximum and minimum is higher or lower than the points surrounding it. So not everything on the graph, just the points on either side of it. These cannot be endpoints. By definition, they have to be higher or lower than the points on both sides. So if it's an endpoint, you don't have points on both sides to compare it to. So if I look at this first one, what would this point be? Could it be a local minimum? No, because it's an endpoint. Is it my absolute minimum? Yeah. So that's the absolute min. What would this one right here be? Local or absolute? Local max. It's not the highest on the whole graph, but it is higher than the points on either side of it. What about this one? Local min. This one is absolute because it's highest on the graph. Is it also higher than the points on both sides? So this is technically both. It is a local and an absolute max. This would be a local minimum. So we did these in college algebra. We just usually didn't have quite so many in one graph. But we would look through and identify all of those. And we had the same definition. The absolute could be endpoints, but the locals could not. All right. So far, so good? There's a second graph right there that just shows, again, local min, local max. This is both the local and the absolute minimum, so it can be both. So let's look at another example. I want the maximum and minimum values of f of x equals x squared. Identify each as local or global. What does x squared look like? Just your parabola, isn't it? So this point right here would be what? A local min. Is it also an absolute? Yeah. So it is both the local and the absolute. Do we have any maximums on here? No. Because the ends are going up forever. What about x cubed? That's the chair. So what about this one? It doesn't have any because it keeps going forever there. Let's look at this one. I apologize. That is really dark. I know that's hard to see. I don't know if I can. Not gonna help a whole lot. Okay, so if you can't tell on here, we have an open circle. So it's like a line, open circle. Sorry, this is what happens when I try to steal pictures from somewhere else. You can't see them very well. Okay. I want all the maximums and minimums. So you are going to have two problems tonight like this. So let's list out. We need absolute maximum, local maximum. Absolute max is the single highest point on this graph. what would that be? 4, 3. Do you want me to write it in the function notation or just as an ordered pair? Ordered pair. So my absolute max is 4, 3. What else would that point be called? It's the absolute, but it is also a local because it's not an endpoint. Do we have an absolute min? No, the lowest point of my graph is an open circle, so there is no absolute min. Okay, let's go through and see what else. We have one local max so far. Let's go through here. So this open circle can't count for anything, but notice right below it there is a closed circle. What would this closed circle be? It is one of those 4 things. It's a minimum. It's a local minimum because the points on either side of it are both higher than that. The points on either side are up here. This one's way down here, so that is a local minimum. -4, -2. All right, and we're traveling. What would this point be? A local min, -2, -3. This one. Yeah, even though there's a break in the graph, it's not the endpoint of my entire graph. Is it higher than the points on both sides of it? Yeah, so that is a local max. So that would be at 0, -1. Can this point count for anything? No, because it's open. Can this one count for anything? No, because it's open. Okay, here's a closed circle. It's higher than the points on the left, but is it higher than the points on the right? Nope, so that's nothing. We already did this one. Can an endpoint be a local maximum? Nope, so we're done. Is that okay with everybody? Let's see if we can draw a graph to meet some requirements. So I want a graph that has an absolute maximum at 5. That 5 is referring to the y value. So the highest y value my graph ever hits is 5. An absolute minimum at 2. So this graph, basically the lowest value is going to be at 2, the highest value is going to be at 5. A local max at 3, a local max at 2, or a local min at 2 and 4. We got a lot of stuff to do here. Okay. Can absolute maxes be endpoints? Yes. So my highest point would be at 5, and that could be an endpoint. My lowest point is at 2, but because I said that's also a local min, can it be an endpoint? No, so I'm just going to put one somewhere, but I know my graph has to start before then. I have a local max of 3, so somewhere I have to hit 3. And a local min at 4. Okay, so let's see if we can draw a graph. So this is my lowest. We need a maximum here of 3, a minimum here, and a maximum here. This can't keep going because then I wouldn't have an absolute max. So that is one such graph. Any questions there? So let's kind of run through some things. extreme value theorem tells us if our function is continuous on a closed interval, so between these 2 points it's continuous, then the graph will have an absolute max and an absolute min somewhere in the interval. Okay, if you've got a closed interval, that means you don't have arrows going forever. You have a starting and a stopping point. So if you have that, you would have to have a maximum and a minimum in there somewhere. I put some graphs kind of showing that if you have those starting and stopping points, here's an absolute max and absolute min. Absolute max, absolute min. This one, it has 2 absolute maxes because they hit the same y value, 1 absolute minimum. This only works if your graph is continuous on that closed interval. If it's not continuous, if there's a break in the graph, we can see this one right here. Does it have an absolute maximum? No, because I have an open circle right there. So there's no absolute maximum. This one, there's no absolute minimum. And also, it's not a closed interval because I ended on a vertical asymptote. Does it have an absolute max either? No. So that only works for continuous functions with no asymptotes in them. So then we need to ask ourselves, how can we get those values? So if you think about a graph, those maximums and minimums are the peaks of our graph. What's true of those? If I drew those tangent lines in, what kind of tangent lines do we have there? Horizontal. What's the slope of a horizontal line? 0. So how do you find the equation or the slope of the tangent line? We've done this. What do we do to find the slope of the tangent line? Derivative. So to find maximums and minimums, all it is where the derivative is 0. Haven't I asked you some maximum questions before? Like, what's the maximum height? And you would set the velocity or the derivative equal to 0. So with these, if I'm asking maximums or minimums, we need to find those points where the derivative is 0. That actually has a name. It's called Verma's theorem. You don't have to memorize that. But it just tells us that if that point exists, the derivative is 0. Is it possible to have a horizontal tangent line and not a maximum or minimum? If you think about x cubed, okay, if you did the derivative, what's the derivative of x cubed? 3x squared. I want to know when that equals 0. So if you divide by 3, x squared equals 0, so what's x? 0. So this tells me we have a horizontal tangent line at 0. Is there a maximum or a minimum at 0? No. So we will find everywhere the derivative is 0. That doesn't mean the point is a maximum or minimum. It means it could be. So we will have to look to see if it actually is or not. Another situation to look at. Let's talk about our absolute value function. Can we agree this is an absolute minimum? But remember, when we did the derivative of this, before we did the derivative of our absolute value, we had to look at the piecewise function. And we said it was, if your number is positive, the absolute value doesn't change it. But if the number is negative, the absolute value does the opposite of that. And then when we did the derivative of the first is 1. And the derivative of the second one is negative 1. But we had a problem when we graphed that derivative, because what happens at 0? Does the function exist? No, because those two pieces didn't match up. So we did that back when we were talking about the derivative of the absolute value. And we said it does not exist at 0. Do you guys remember what feature on the graph means you won't have a derivative? Thank you. Yes. Thank you. It's always here to cheer me up when I'm having a bad day. So what's the feature on the graph that makes it not have a derivative there? The corner. Remember we talked about derivatives don't exist when you have corners? So we will have to watch that. That's a place where the derivative isn't going to be 0, but it's still a minimum. So we are finding maximums and minimums can happen if the derivative is 0 or if the derivative doesn't exist. Those are the two places. And so those points are actually called critical points or critical numbers. So that is the big thing we are going to be finding in this chapter. A critical number is anywhere the derivative is 0 or does not exist. And so those are the places where you can have a maximum or a minimum. So can we practice finding a critical number or function? So I want the critical numbers of this. What do I need to do to find critical numbers? Derivative. What is a good option? Anytime you don't know what to do on a problem, it seems pretty likely that you probably need to do a derivative. That's kind of the whole theme of what we've been doing in calculus. What should I do to make this derivative a little easier? We distribute first. Otherwise, we're going to have to do product rule, and I'd really rather not. So that would give us a 4x to the 3/5 minus, this is an x to the first. When you multiply those, you add your exponents. So 3/5 plus 5/5 is 8/5. Oops, that's not f prime, that's just f. So now the derivative. So exponent comes down, 4 times 3/5 is 12/5. Subtract 1 from the power. So 3/5 minus 5/5 is negative 2/5. Minus 8/5 x. If you subtract 1, 8/5 minus 5/5 is 3/5. What do I need to find? When the derivative equals 0. Okay, this looks a bit ugly. Let's kind of rewrite it. What does a negative exponent do? Okay. I'm going to add that other term over. So what could we do? So 8 times 5 is 40, x 2/5 plus 3/5. 2/5 plus 3/5, 5/5, which is just 1, equals 60. So x is 6/4 or 3/2. So my critical points, or my critical numbers, is 3/2, but there is another one. It's anywhere the derivative is 0 or undefined. If you look back at this derivative, okay, let's just look right here. Is there anywhere this doesn't exist? Is there a number I could plug in that would make this not work? Yeah, if you have a fraction, you can't have 0 on the bottom, right? So x can't be 0. Can we agree with that? So 0 is also a critical point. The 3/2 because the derivative is 0. The 0 because the derivative does not exist there. Questions? How are we doing so far? Good. Can I keep going a little bit longer? Is that all right? Not throwing too much at you? So the final step in this section, and I'll probably only do 1 or 2 examples of this today, and we'll do some more tomorrow, is how we use those critical numbers to find our absolute maximum and minimum. So what we'll do is find all the critical numbers, and then we're going to plug the critical numbers and the endpoints into the original function. That'll give you the y value. So the highest y value would be your maximum, and the lowest y value would be your minimum. This only tells us the absolute maximums and minimums, not the locals, but that's okay for now. Right? So we know we can look at a graph and find all of them. If I want absolute maxes or minimums, we have to take all the critical points and the endpoints. Those are the places where they could happen. Put them into the function. Biggest value is the max, smallest is the min. So let's try one of those. I want the absolute maximum and minimum of this function on the interval -1/2 to 4. So, what do I have to do? We have to get the critical points, so we have to do the derivative. So the derivative of x cubed, 3x squared, minus 6x. Is that ever going to be undefined? No, because it's polynomial. So we're good there. But now what do I need to find? So we could take out a 3x, and that leaves us with x minus 2. So x could be 0 or 2. Those are your critical points. Now we have to find the maximums and minimums. So we have to take the endpoints and our critical points and plug them into the original function. One thing, if I had gotten a critical point of like 6, would I use that here? Why? Because I'm only looking between -1/2 and 4. So if you get a critical point that isn't in the window, you just throw it out automatically, because we're only looking for the ones between those numbers. So we're plugging these into the original function. All right, so if we put in -1/2, we get what? -1/8 minus 1/2, -1/2 squared is 1/4. So -1/8 minus 6/8 would be -7/8 plus 1, so plus 8/8 is 1/8. If we put in a 0, 0 minus 0 plus 1 is 1. If we put in a 2, we get 8 minus 3 times 4, so minus 12 plus 1. So that's -3. Put in a 4. 4 to the third, 64, minus 3 times 16, so minus 48, plus 1, and that gives us 17. So, what's my absolute max? What's my absolute min? Now, is that necessarily for the entire function? No, just in between -1/2 and 4. So just on that section of the graph, we got our maximum and minimum. Let's go ahead and look at the next example. Does the function f of x equals 2x attain a maximum and minimum on the interval 0 less than or equal to x less than 1? What's wrong with this interval, first of all? We had a theorem that told us we have to have absolute maxes and minimums if the function's continuous. Is 2x continuous? Yeah, it's a polynomial. And if we have a closed interval. What's wrong with this interval?
It's open.
It's open on one end. If you graph this, if you put in 0, 2 times 0 is just 0. This is just a line. When you plug in 1, you get 2, but what kind of circle would that be? Open. So this graph has an absolute minimum at 0, 0, but no absolute maximum because that interval isn't closed. So we do have to have the closed interval for it to work. That's one of the two conditions. The second condition was that the function had to be continuous, so I want to show you why that's necessary, and then I'm going to stop for today. Okay? So example 5, I gave you the closed interval. I want to know if this has a maximum and a minimum. Let's look at a graph. Let's graph the second piece first. 1 if x equals 0. What's that? A point. 0, 1. 1 over x if 0 is less than x is less than or equal to 1. We can't even plug in a 0 because 1 over 0 is undefined. So that's like a vertical asymptote. If you put in 1, 1 over 1 is 1. If you put in like 1/2, what's 1 divided by 1/2? 2. If you put in 1/3, you would get out 3. It just looks like this. So does that one? No, it has an absolute minimum, 2 of them actually, at 0, 1 and 1, 1, but no maximum. So again, for this to work, it has to be continuous and closed interval. And I just showed you an example of each why, if those two requirements aren't met, we cannot do this. Okay, so on these, just follow the directions. It only asks for the critical points. You don't have to do maximums and minimums today.